Good evening, everyone. Welcome to the very last Tecnoglass series, lecture of the spring series. I'm Joel Lemire, curator of the series, and obviously the director of the graduate program here at University of Miami School of Architecture. Tonight we welcome Philippe Block, who is really the perfect character to round out this series. Before I introduce him, I need to spend a moment reflecting on the series as a whole, and in particular on the support of our sponsor Tecnoglass. For 2 semesters now, I've been fortunate enough to curate a collection of thinkers, designers, and architects whose insights have been invaluable to our intellectual culture here at USOA. It has really, frankly, been a joy and a privilege to get to do this, to say, you know, like, I really like this person's work, I'm going to bring them here. All, of course, enabled by the generosity of our sponsors. So thank you very much to Tecnoglass. Finally, one piece of bureaucracy before we get moving. Those seeking AIA continuing education credits need to email our coordinator, Stephen Fett, at sfett@miami.edu. All right, to the task at hand then. It's no surprise that I would seek to include Philippe Block in a lecture series entitled Operating in Material Conditions and Architectural Imaginaries. The premise of which is that to, quote, accomplish the revolutionary changes required of a responsible architecture, we must reinvent the matter that constitutes it. The material reconstitution operates along many axes at the scale of production, composition, geometric deployment, form, and structure, end quote. These questions, geometric deployment, form, structure, these are clearly in Philippe's wheelhouse, right? The Block Research Group touts, for instance, quote, strength through geometry as a driving principle of their internationally recognized research. And so for me, he had to be here, or we just weren't going to have the complete conversation. Philippe plays an essential role in this discourse, and his research has been incredibly influential, both on me and my students and a generation of students. But I have to say, for me, part of what makes his work so compelling is actually in how distinct it is from his contemporaries, namely in how it views both the past and the future. It sounds vague, but hear me out. The post-digital critique of the computational turn has rightly pointed out that when some claim that this moment, our moment, is wholly new and completely untethered from the past, it loses too much. Philippe Block, despite the fact that it's doing bleeding-edge computation and technology that suffuses his work, but in contrast to those sort of die-hard digitalists, constantly recalls the past. So long-standing techniques of graphic statics are refigured to serve in parametric vault definition tools such as RhinoVault. Guastavino's tile vaults are distorted and generalized to account for variable conditions along the ground. Nervi's ribbed floors are re-energized with precision and intricacy. So Philippe's work is distinctly contemporary, but with the flavors of longer histories. And in the future, perhaps we should ask Philippe about it, but I would argue that this dedication to compression-only structures, for instance, offers a vision itself of the future. As our resources become more sparse and destructive habits of extraction become untenable, the material palette available to architecture will inevitably veer away from highly processed matter like steel. But Philippe's structural forms owe more allegiance to geometry than to material. They maintain, in fact, are stubborn in their behavior, even with the most primitive materials. You can contrast that with a couple of other speakers in the series who have very different ideas of the treatment and processing of the material. For instance, Regina Sanfratello, who spoke at the beginning of our series, who proposes that all materials should be ground essentially into powder and then redeployed through 3D printing. And then you have at the other end of that spectrum people like Brandon Clifford, who want to cannibalize former structures, carve into them in somewhat restrained ways, and then make rough stacks out of them. Philippe is clearly proposing something very different in his work, that even at the end times, this knowledge is productive and its products carefully calibrated. Okay, so I've said all this without even mentioning how influential and recognized Philippe Block's work is. He reaches everywhere. The objects are spread worldwide, including Mexico City, New York, Seoul, Switzerland, and of course, were exhibited to much acclaim at the 2016 Venice Biennale. There was a small shell actually in the fabrication yard at MIT when I taught there, that was put up with the help of a couple of my students at the time, at the expense of their studio project that semester, I would add. So you owe me something for that. He's also taught all over, currently at ETH in Zurich, but also in workshops at Tongji University, MIT, the Bois Boucher in France. And his accolades are many, including recently the Rössler Prize for Most Promising Young Professor at ETH and the Berlin Arts Prize, both in 2018. Well, we're very lucky to have him here. I'm really looking forward to seeing this presentation. And so on behalf of the School of Architecture at the University of Miami and on behalf of Tecnoglass, please join me in welcoming Philippe Block.
Thanks, Joel, for the invitation first and foremost, and also for this very personal and beautiful introduction. The expectations are there now. So before going, I want to maybe talk a little bit about the title. I don't know how it is in the US, but in Switzerland, putting concrete in your title or a material that you work with is not done anymore. So there is absolute concrete shaming going on. And so I put this title now, this word explicitly always in the titles of my presentation, because I really believe that we need to go towards a much more nuanced discourse on sustainability. And so you can see it as a provocation, and hopefully at the end of the lecture, you will see why I wanted to start with this provocation. So maybe first framing what really drives us, and it becomes a quite anxiety-driven straitjacket increasingly, is the tremendous challenge that we have to provide adequate housing and infrastructure for over 2 billion people. That will be more people more that will be on our planet in the next 20, 30 years. You must have heard calculations like this, that in order to provide that, we will have to build the equivalent of one New York City every month for the next 40 years. I truly hope that we will not be doing it like this. I use this as an image of an industry that is outdated and that has barely evolved in the last century, with this as a result, that we are responsible for 40% of the man-made greenhouse gas emissions, 40% of virgin material use, 40% of waste production, and then the one that typically is better understood by the general public, also a huge energy consumer. So when I talk about us, I'm talking about construction and building industry. So I hope with these few slides, I first and foremost hope that I'm preaching to the choir, but secondly, that you agree at least that there is a need, a desperate need, in fact, to change the way we both design, but also build our structures. And I will also be talking about how I truly believe that those two aspects will have to come together. As an architect engineer, as a structural designer, I will mainly be talking about embodied emissions. So all the emissions, greenhouse gas emissions that have something to do with the making. So everything until you turn the key, you start using a building. I will focus less on the operational emissions, but there has been so much research done in that field, so much funding going to that field. And also, honestly, or perhaps said a bit cheekily, or yesterday someone said that that doesn't make sense in the US. Cheekily is a British word, so hopefully you understand what I mean. But we have a solution: just use green energy, use reusable energy, and so then you solve the operational emissions directly. But we don't have such an easy solution for the embodied emissions, and that becomes truly the bottleneck going forward. I promise that this will be the only equation. I might come back to it once again, but I like this equation because it really it breaks down what really matters when you want to try to address those embodied emissions, which you could look at as the the global warming potential. So this equation that I borrowed from my colleague Catherine de Wolf and extended, in fact, a bit, shows that what we should look at is we take all the parts in a building, we add all of their contributions, and then what you see what matters is the mass. So that's this M. What also matters equally is the embodied carbon coefficient. So this is a a value that is calculated to represent the amount of emissions or pollution of a material. And then lastly, time. So the lifespan of, ideally, we want to extend the lifespan of a building, a component, or resources. And that's where circular thinking comes into play. And I will talk about this later a bit as well. So, but I want to start with this equation because there is a lot of misconceptions about this. There's still, surely in an engineering kind of context, there's still the belief that lighter is better. But if you achieve lightness with high impact materials like carbon fiber, for example, then you're offsetting everything what you might achieve in lightness. So as already introduced by Joel earlier, we try to be part of hopefully a solution by introducing strength through geometry and material effectiveness. And I will explain both through a couple of our projects, and then this will all nicely come together at the end. So first, strength through geometry. Again, already mentioned, the armadillo vault is perhaps one that I want to show in this context to clarify what you can achieve when you get the geometry right. So this is what we showed at a 2016 Venice Biennale. What you're looking at are 399 cut pieces of stone, very simple stone, limestone, that are held together just by gravity, by geometry. So no glue, no mortar, no reinforcement. So what we wanted to do with this project is we wanted to bring back or show that perhaps we have forgotten some essential knowledge that make these beautiful structures stand for centuries. And here the specific fan vaults of King's College. If you calculate their thickness over span, then they are proportionally, literally as thin as an eggshell. So these structures also are standing without our typical reinforcements and high-tech materials and so on. So that is what I initially did for my PhD with John Oxendorf at MIT. I developed these methods to assess historic structures. But then in my research group, we started to translate these tools to discover structural form. And we did this indeed through graphic statics and three-dimensional extensions of graphic statics. We made tools to have other people discover the beauty of compression, that is not just the boring dome, but there is much more geometry to be gotten. Just, I added this to give you a little bit of an insight that even though I'm emphasizing the power of geometry, it was a beautiful also project of rediscovering or translating historical principles of stereotomy that Shirley Brandon talked about into a computational framework that offered us an opportunity to realize this structure in just a couple of months with a reasonable budget. And so here's some of the details of the very specific fabrication techniques that we developed to speed up the process, but that we then really used also as an aesthetic opportunity to make this unique shell. So here you see our colleagues from the Escobedo group out of Austin, Texas, dry assembling the geometry. So I didn't want any mortar or anything because there's too many skeptics around, and surely someone would have said that it's the mortar that is keeping everything up. So that's why we went as extreme to assemble this 3D puzzle just with dry connections. As mentioned, what we like to try to do is to let the fabrication and the structural constraints speak and become an aesthetic by themselves. So here, for example, these planar interfaces on the outside had to do exactly with a fabrication optimization, that we never switched or moved a piece around because that was too costly, too time intensive. That's where tolerances could appear. And then these interior kind of roughness had to do with only describing this internal surface with a rough cut and then hammering it away and leaving that then to express the global flow of forces. But the reason why I show this project is not only because I'm proud of it, but mainly also because I want to, again, this image, maybe we wanted really to shake up the architects and engineers that we should reintroduce structural form to activate humble materials in a safe way, like we used to be able to do, like the master builders used to be able to do. So what you see here, this 2 inches of stone touching, is a first kind of hint at why I care about good structural form. You can significantly reduce the mass indeed. A second project that I was only towards the end involved, but very luckily involved by Peter Rich architects, John Oxendorf and Michael Ramage, is the Mapungubwe Interpretive Center in South Africa. I was lucky to be involved. The new tools that I developed for my PhD, trust network analysis, were used to do the safety assessment of all these vaults to give the engineers the courage to indeed go for a fully unreinforced structure based on local resources. These vaults, these structures were a reinterpretation or bringing back of indeed the Guastavino vaulting. So here maybe you recognize the oyster bar in Grand Central Terminal. What's amazing about this style vaulting is that it's not only 3 layers of unreinforced style that achieves these large structural shapes, but on top of that, using a Mediterranean technique, you can build it in stable sections using a fast setting mortar. And you can imagine that not needing a descriptive or a full formwork to build this structural geometry was very important for a site that was literally in the middle of nowhere on the border with Zimbabwe. So here you see the timber here is only guide work to guide these local laborers that a week before were carpenters and farmers into this new technique. So here the first shell that they managed to build literally with only local resources, not only local materials, but also local labor. The local materials was just pressed soil, so unbaked tiles. For this specific soil that came from the site, 7% of cement was needed to stabilize them so that they would be just strong enough for the purpose. But I'm showing you this project because this is still one of the most eye-opening moments in my career, and it's still driving a lot of the things that we're doing right now. The difference between those 2 images. On the right, the women of the village there are carrying the tiles in very small packages. And the reason for this is that these tiles are so weak that you can just snap them in bending. But they take peanuts in compression. They take about 10 to 15 times less than a standard construction concrete. So they're only designed to take compression. And you see that these weak tiles that no one today would consider structural material, if you place them where the forces naturally want to flow, these become indeed safe materials, as we used to build our constructions in the past with vaulted kind of geometries. So how that works is that an arch is a good geometry for a certain loading case, but we also need to take some live loads like users. And so the red line here represents where naturally the forces would want to flow in compression. So you see that here we don't stay within the section, so that would literally mean collapse. So that means that you need a stiffening scheme. In the first project, the Armadillo Vault, we had this double curvature that actually gives you that stiffening for live loads. In these shallow kind of structures, you need to do something else. So here, for example, these stiffening walls were, these spandrel walls were added, and you see effectively in principle what it does. It provides a direct load path for the compressive forces to go to the supports. If you then add a tension tie, what we just did in the last 20-30 seconds is we basically provided or rediscovered or brought back a perfectly viable alternative for a reinforced concrete floor or beam, but one that uses 70% less material, right? So there is no rocket science here. This is just bringing back these principles, but in a context of indeed resource scarcity and emissions and so on. This is for me an important starting point. And as you see here, this floor is happily still the structural component for the floor of this museum. But what I forgot to say is that another thing that you get by placing material naturally where it wants to be is that the stresses in your structure are very, very low. And this is also an important aspect because there is almost a one-to-one relationship between how emitting, so the carbon footprint, and the stresses of the material are the same. So by getting the geometry right here, we could just use this local soil, these weak materials with peanuts of cement kind of added. And so that means that a second reason to get the geometry right is not just to reduce the mass, as I said, that is only part of the equation, but also to reduce the stresses in the material and to be able to activate very weak, very low impact materials. So all of these kind of ideas we brought together, and in the last Venice Biennale, in collaboration with DIT Architects, the computational design group, we wanted to show these same principles on a material system that is very much en vogue, which is concrete 3D printing. So what you look at here is an unreinforced masonry, so fully unreinforced concrete 3D printed structure. The reason why, well, first I want to emphasize that there is absolutely no reinforcement, not in the material, not in the global structure, and so on. And the reason that I wanted to bring this message in this kind of context is because I consider concrete, so not reinforced concrete, but concrete as an artificial stone. And a stone is happy in compression. A stone wants to follow these logics of indeed masonry systems. So for this project, we use masonry on 2 levels. Globally, it's discretized like a Roman arch, for example, a Roman bridge or viaduct. But also on the level of the 3D printed components, every single layer is layered such that it is as orthogonal as possible to the dominant force flow. And this is an important aspect because in most of 3D printing applications that you see, the designers are from the beginning fighting against the natural delamination that happens in between those layers. So if you get the geometry right and you place the layers where naturally these compressive forces want to be, you actually can use these beautiful 3D printed synthetic stones. In a way, you can use them directly structurally and not just as a glorified formwork for a high performance casting concrete structure, reinforced concrete structure. I'm blatantly attacking most of my colleagues in this field, but that is the point that I wanted to make with this project. So we used all our tools that we developed for assessment and design to then design this bridge. But we also use state-of-the-art concrete 3D printing. So this is called 2-component concrete 3D printing, which allows you much more control. And as you see, these non-parallel kind of print layers with non-uniform layer thickness. So it's in 3 dimensions warping. How we approach these projects is that also a bit untypical. So I want to quickly talk about it. We don't first design a structure, then discretize it, and then hope that all the layers will not collapse and work and so on. We actually, and this is the work of Shajir Bhushan, that's also the link to DIT Architects. He's the head of their internal research group. So that's always a good collaboration when you can boss around your collaborator because he's still finishing his PhD on this topic. But what I wanted to say, too many distractions, I'm trying to entertain myself. What I wanted to say here is that we actually encode all the fabrication and structural constraints in the print path. And so that means that whatever we generate is both structurally and fabricationally feasible. So that means that we treat geometry implicit and the print path explicit. And so that is an exciting kind of other way to look at design. And by doing this, that we can really capitalize on all the promise of 3D printing, that you place material only where it's needed. So you see that also on the inside of these voussoirs, these 3-dimensional kind of elements, we lighten them up. And on the right, also precisely where needed, because you see that indeed all these print layers are laid such to be aligned to the force flow. Perhaps an interesting aspect is that I talk mainly about environmental aspects, but we also want to crank up our productivity to faster deliver kind of solutions. And in that context, it's exciting to share that these 53 blocks for this in diagonal 20-meter spanning bridge were all printed in a total of 84 hours. So that is actually a nice aspect as well, that you can start to rethink the order of things, that you can spend much more time on design, development, engineering, because you have everything is connected and synchronized. And so the cranking out of the geometry at the end is quite efficient. I want to maybe, again, like I tried to do in the armadillo, give a little bit of detail on the fabrication. So here, for example, in the initial design, we wanted the bridge to be by itself, so no deck on top. And so the top layer would then also need to be able to take point loads. So for example, of people walking on it. For the specific material that we got for the concrete ink, the 2.5 centimeters that would naturally come out would not be sufficient. So we needed to double up the top layer only. And so here you see what happens. In this case, a very undesirable kind of situation of this very pronounced kind of feature in the middle. So through prototyping, we saw that this is something that we wanted to avoid. And so here it was decided to turn around at every single internal aspect to then effectively, as you can see on the top, end up indeed with this doubling of the layers. You will see later how we use that then in the shaping of the structure. But because material only placed where needed, this was a very easy job done by my team together with only 2 professionals. Very quick assembly, dry assembly, as indeed a dry assembled or equivalent to a stone cut kind of masonry system. And here you see that also the balustrades were kind of dry assembled. For me, I was excited to show this project because I wanted to share these messages. Too often we focus just on reducing. So that's the aspect of placing material only where needed. But an important aspect that we are showing here as well is that by separating compression and tension, by having an unreinforced compression only arch and then a tension tie, we have a very straightforward repair strategy. And in a context of infrastructure and the embedded reinforcements that cause corrosion and very fast decay, a topic that is very, very relevant here in the US, of course. This is perhaps an aspect to look at. Secondly, because of the dry assembly and because of the masonry logic gives you a nice locking of your geometry, the pieces come naturally together without needing a chemical or even a mechanical connection. One could, in general, so not necessarily for this bridge, like that we would be reusing this bridge, but for prefabricated components in general, this is a very powerful kind of outlook of being able to reuse the components. And then lastly, recycling, which we did do for this bridge, because it's now taken apart, recycled, and it will be 3D printed again. So there will be a Striatus 2.0, which is called Phoenix, because it will literally return from the ashes of the original one. And this one is now being designed as a permanent structure. We have another commission for a permanent structure as well. But I wanted to quickly talk about recycling. Again, the same ideas of separation of materials. So you're not polluting your resources. You can easily take it apart. So you have a dust-free kind of demolition opportunity as well, and easy, low threshold, no excuse also recycling. So all of these things were layers, striatus layers that we wanted to show into this project. But here maybe some nice shots, like for example, these little traces that we then controlled globally. They actually come from the stiffness on the inside. So it's the nozzle changing direction and slightly perturbing the outside layer that was already printed. So these kind of accidents, there were accidents maybe the first time we did it, but then we recognized the design potential and globally then controlled these features to add a bit more tectonic kind of reading to this element. And then I talked earlier about, again, a fabrication necessity where we started to turn around the layers. You see here how we then use these kind of seams to also express the dominant force flow and to give that additional reading to the structure. Maybe a nice detail here is that the 2 little rascals are the 2 kids of my right-hand man, Tom van Mele, with whom, or maybe more my partner in crime for all the crazy things that we do together in a research group and in practice as well. So, but here with this image again, kind of showing you this masonry on two levels in the global discretization, but then extremely important also on the very careful layer deposition orthogonal to the force flow. And so I try to argue here also that this stands as, of course, a very kind of extravagant, but there is many circular thoughts that we wanted to clarify that naturally come from this discrete masonry kind of logic. I already talked about collaboration with Zaha, but also incremental 3D needs to be recognized. Absolutely, these digital crafts, people that do this amazing 3D printing and then holds him both developed the ink and also paid for the project, also not an unimportant aspect. Perhaps a detail here is, again, it seems that 5 months is kind of the timeline of my projects, or 3 to 5 months is somehow how much time I get to crank out something crazy. What's important here is that in these 5 months, we were actively developing the design pipeline, so the integrated computational framework. The engineering tools had to be translated from masonry assessment tools to design tools. A new ink was being developed and tested by Incremental 3D. So all of these things were done in parallel because from day one, we coordinated all the interfaces between all the different partners. And so we did this in a very coherent and disciplined way using Compass, which is an open source computational framework for research and collaboration in the AEC. That is a project that we have been, that Tom has been developing for the last 6-7 years, that now became a full community project with many research groups all over the world working through this. The reason that I want to make this pitch is because the urgency is real and we can no longer afford to reinvent the wheel. So many offices are in their own bubbles, developing their own pipelines and so on. And so through Compass, we share all the tools that we do. We also show how we did our projects. And so we're building up that expertise and wanting others to jump on board and to also share their knowledge as well. So Hilo may be special because it's, except for the African projects, it's the first project that will not be demolished or dismantled after a couple of months. So this for us was a nice victory. It took us a painful 10 years to get there. Perhaps this image clarifies why. It's a bit crazy what we have done. So it's a unit on top of a research building. We try to show a few things. I'll talk a little bit about the roof because it would be weird not talking about it, even though I believe it's not the high impact stuff that we're doing. But what we did with the roof is we wanted to reintroduce these beautiful shell structures. And a key bottleneck in this curved surface structure is how they're being made. So you need all these foundations, scaffolding, an extremely beautiful timber structure that should be the structure by itself, but turns into this after 28 days when the concrete is cured. So this is the promise. And so we wanted to see, can we scale up the academic promise of fabric formwork or flexible formworks, where basically what we want to try to avoid is this brute force traditional way of forcing material where it doesn't want to be. That is where all this scaffolding and formwork and single-use material comes from. And so we want to try to introduce a flexible formwork like a pre-stressed cable net or something like that, and then offer the outlook that you see here on the image. So this is a long-term research where we ended up here with these are some images of the full-scale prototype that was also needed because, well, maybe rightfully so, we also learned a lot in this prototype. So the client thought that these two young Belgians could not be trusted to directly build this craziness. So we had to demonstrate it with all partners and pay for it ourselves, by the way, to realize this. So we developed this kit of parts, then this fabric allows to cast on top. We developed these systems that really could be done by typical industry partners. And then there it was. So this was the prototype of the roof. It still took 3 years after this then to finally get on site, but then here finally we could then get on site. The same kit of parts, by the way. So we indeed developed something that could be entirely reused. So even though the geometry of the prototype was significantly different to the final one, another color appeared, and then finally the casting of the first shell. It is a 2-layered shell, so it's actually a unique, just over an inch, twice 1 inch of concrete that works a bit like a doubly curved sandwich structure. We have concrete going from the inside to the outside, so you see some features like these facade details appear. The insulation in between, which allows this flying concrete from the inside to the outside without thermal issues, without thermal breaks. And so this was after decentering. And so there it is now still empty, but it will be quite a funky office for someone. What I want to highlight maybe here is that, okay, I forgot to make the disclaimer. So this project started 10 years ago. As a young academic, I thought this was the future, cool, this is what we needed to demonstrate and so on. I'm still happy that we did it because it shouts at you and people are curious, then come and then they listen to what really matters. You will learn about this next. But one of the key things nonetheless that we did is that we achieved this project to be on site, done by normal industry, normal concrete workers and so on time, within budget, and within 1/8 of an inch of precision in concrete construction. And so why this was possible is because we reduced the complexity to this one node. So we developed this node that we then use to measure where things are, to nicely interface all the elements, but also to break up this craziness into 40 by 40 centimeters, little patches that are practically straight and very simple. And again, you have all these little node elements that tell you your structure should be that thick there, your reinforcement should be connected there, and so on and so on. So this is the maybe one thing that I wanted to highlight that allowed us to do this. But also, again, this was the first project that from A to Z, including all the coordination on site, was done through Compass. And okay, many people do sophisticated BIM, and our partners call it BIM on steroids, which is maybe a nice kind of clarification on what we're trying to do. But why I want to nonetheless say this is that why it is beyond BIM is because it also allowed totally new algorithms and measuring techniques and new research to be introduced in a real project that was done with typical practice, many of which have absolutely no digital expertise, have no experience with doing complex geometry. So this was really essential to do that. And I'm very proud to say that we had absolutely no clash, no conflict, nothing happened on site. And the reason for this is this diagram, is that we don't pass on models to everyone, but we have a central computational geometry and coordination kind of hub that sends all the information from that source to all the partners. So there cannot be any conflicts and clashes because it always comes from the central core. Maybe I'm emphasizing this a little bit too much, but through explaining a little bit how we realize that, I do very strongly believe that we also have to rethink the models of collaboration, and we do this through computation. In this context, I allow myself a quick sidetrack to NIT Candela, which we did in Mexico City, again with the same code group, with the computational design group of Zahadid architects. The name already kind of hints at what we try to do. So Candela, the Felix Candela, the beautiful shells in Mexico City. But again, also there, they need all that formwork. He was very smart to stick to high part surfaces so that you can describe them with straight lines. So all this wood can actually be reused or in another side, but you still can imagine the logistics, the labor cost and things like that. So what we did in NIT Candela, very similar to Hilo, but at another scale, is we used literally sweater material. So we did a technical 3D knit that served then as the formwork of the structure. This was the work of, she's now professor in Delft, of Mariana Popescu, and then for a former colleague of Lex Reiter. So Lex was our concrete magician that developed a stiffening paste that turned this sweater into something that is just stiff enough. But so here you see on the top right, Mariana knitting arguably the longest scarf in the world that then could be nicely vacuum packed, and it weighed only I think 40 or 50 pounds. I'm not good at the count, so 25 kilograms. And could be brought on site just in time to then have the very craftful local Mexican concrete finishers actually then realize the shell. There's some details that are maybe interesting, that the little balloons created these pockets so that the final shell was not just a thin shell, but a shell with stiffeners running in two directions. This was to make to increase the structural depth without adding mass, so that it could be realized in this inner courtyard of the MUMAC. So here you see we left in this case, we left the fabric formwork as a stay in place feature, so to kind of break with the coldness of the concrete. But here you see this duality between the two. And from the top, you then also see indeed again how thin this structure was. So this is really also about realizing structural efficiency, but not at the cost of all this formwork and all this kind of labor and cost associated to it. So here, even though a very small project, I think the numbers are pretty cool. The shell is about 500 square feet of concrete that adds up to 5 tons. And then except for the reusable external scaffolding that we had, the cable net, all the connections, the knit and so on, including the stiffening paste, cost only $2,500 US. As I said, weight less than what you can take in a coach from Switzerland to Mexico City. And then perhaps what's interesting is that if you were to mill such a formwork, then you would be milling for 3 months non-stop. The 3.5 months on the bottom was between the email by Zaha, like, do you want to team up for this exhibition, and the opening of the exhibition. In that time, we had to develop the system, do all the design iterations, the engineering models had to be calibrated and run over all the parametric settings. We had to go on site, work with a local crew that even the language was new to us. And so the entire knit was realized in a total of 36 hours of continuous knitting. All right, so sidetrack, let's go back to Hilo. Because this large shouting shell was there actually to have people pay attention, and I want them to pay attention to the floors. So let me quickly give you the framing why I now want to finish with our floor research, even though it's probably the most banal and silly element that we nonetheless all need to work on, why I'm so excited about what we're doing there. So one of the reasons is that, I mean, we talked about this one New York City every month for the next 40 years. Another calculation is that this translates to roughly 2,000 billion square feet to be built again. So I want to tackle these, and particularly for the medium high rise. So for the 10 to 30 story kind of buildings, a very common typology in a densification of buildings, even in Switzerland. This is now a typology that is becoming very common. But if you look at these medium high rises, then you notice this, that if you look at the distribution of the mass of these structures, then you see that 3/4 of the mass is in the structure indeed. And for me as a structural designer, this was not only eye-opening, but also entirely kind of unbelievable, because this suggests, and it is like that the structure is mainly there to keep itself up. So not to users, not all the things that actually matter, but just to keep itself up. If you then zoom in a bit more, and by the way, so Bill Baker, with whom I'm teaching at IIT, said that if you look at all the skyscrapers in Chicago, we are talking about 50 to 60% is in the floors. So meaning again that this is even conservative, because we have medium kind of high buildings. So, but what this tells us is that the material intensity, the real bottleneck when it comes to all this emission that all these buildings are generating, is really the floor indeed. And that is where I now want to switch and talk a bit about the other term. I was talking not about material efficiency, but material effectiveness. And we put another term there because we wanted to avoid that confusion of the efficiency is often kind of related to lighter, to less, and so on. While effectiveness has to do with using a material how it wants to be used. And that is where maybe now it's appropriate to address the gray elephant in the room. So that concrete is, everyone seems to agree that concrete is the most destructive material on planet Earth. It's probably true because it has been used in bulk. It has been used all over to build our entire world. And it also is being used inappropriately. So I will come to this later. But I want to question this statement because you will see later on that just focusing on the material and just plainly say that wood is good and concrete is bad is an entire absurdity. It's indeed how you use the material. Here, maybe a few kind of hints, not proof, but hints. If you look at the energy kind of side of unit mass of materials, this is a logarithmic scale. So that means that it exponentially increases. You see concrete all the way on the bottom. On the right, you will recognize some kind of steels and things like that. But if you look at what really matters, the embodied carbon coefficients, then there also you see that concrete is on the bottom. So clearly it's not an issue of the material. The material actually by itself per unit mass is extremely good. So what is going wrong? You probably can imagine why I gave you the framing of strength through geometry and masonry kind of systems. Is if you indeed consider concrete as that artificial stone that it is, then these kind of these kind of geometries make a lot of sense. And to be more specific about what I said earlier, it's not just the global volume. It's not just on the concrete that you save. So here on the left, that's what we all do, right? We force a material to be in a geometry it absolutely doesn't want to be. And by doing that, we use 70% too much concrete, but also 90% too much reinforcement steel. So by introducing, as I said in the beginning, these kind of geometries, you achieve these numbers. So that is then what we have been developing in a 3D way. So rather than just an arch with stiffeners, we have a 3D vault with stiffeners that accumulate to the corners so that we only need super thin tension ties around the perimeters. And an early model then really shows these two aspects. So the vaulted geometry for the dead load and then the stiffeners for the live load. Also, a similar thing as what we did in Hilo. So Armadillo Vault was shouting like, look at me, craziness, right? But actually these floors were already shown at his exhibition as well. And those are the ones that really matter, I believe. So those were very early prototypes. And one of the prototypes was 3D printed, sand 3D printed. So a similar material to the weak material we used in Ethiopia. So peanuts in compression, really. But you can, if you take any piece out here, then you can literally break it as easily as cold dark chocolate, of course, the superior Belgian one. So we took then the sister, so there were two of these models. One we still have, the original one, and the second one that we printed is the one that we demolished. We did the entire required loading protocol to demonstrate indeed that this would be a safe structure for use. And perhaps 1,200 kilograms of ETH nerds standing on a 2 centimeter unreinforced structure with material properties equivalent to cold dark chocolate is perhaps a bit more visually convincing at least. But so initially when I showed this in lectures, then of course all the engineers just started to attack me. That this has nothing to do with modern engineering robustness, this and this. And luckily, actually, what I am suggesting is nothing new. Yes, we are developing new computational methods for design and engineering. Yes, we now have digital fabrication that allows us to realize these non-standard geometries at construction scale at a competitive kind of price. But we have history with us, right? Because what I didn't say about the oyster bar is that it's not only built without formwork, it's not only 3 layers of unreinforced masonry, it has the same material properties as the 3D printed structure that we've had, but these shells are actually carrying the Vanderbilt Hall on top. So if you think that what I'm reintroducing here is entirely crazy, then perhaps we need to warn millions of New Yorkers going to work every single day that they are in danger of dying. So that is then what we did in the floor. So we have this 3D floor. It's the first one that got built. And with this, maybe a small sidetrack, the importance, not just of prototypes, not just of demonstrators, but here having an opportunity to really build this was essential to accelerate this. And so this floor is roughly 16, 17 feet by 17 feet, roughly. And the structural thickness is just over an inch, so 3 centimeters of unreinforced concrete, low strength concrete, right? Because we want to have low emissions as well. We use 50% of aggregate and cement replacement from construction demolition waste. So all of this is possible because we get the geometry right, because it is, the stresses are so low. So we got it through approval and so on. For practicing architects, and particularly in Europe, this is probably the most spoken or the most important topic. It's acoustics. What's super exciting here, and I sound perhaps a little bit too much as a salesperson at this point, but it all is coming together, it's all nicely congenial, is that rather than adding mass, which is the typical way to deal with contact noise, with low frequency airborne sounds and so on, what we always do is adding mass. What we had done, this was long-term research of Thomas, he's now professor in Washington, is actually to use structural geometry, stiffness, to absorb these problematic vibroacoustical kind of artifacts. And this was again great about doing this in this project, because even though we did the research, all the acoustical tests with experts, right? So not just our group, we team up with experts and so on. Clients, big real estate developers, they're not interested in academic papers, right? So this is cool that we can go there, and I asked them to come with more than one so that one of them can go on top and start jumping around, and that indeed is 3 centimeters of little material is indeed doing the same as adding the typical mass that is suggested in the building codes, right? So also here, geometry helps us to really hit that performance criteria, which is exciting. I'm almost there. I want to zoom out again, because this is just one small project, right? But why I believe so much in this one small project is, let's go back to these towers, right? That we see pop up all over the world, in the developing world, but also in other places. If you take any of them, for example, 25 stories high, let's kind of see what happens if you swap your typical reinforced concrete floor, and it's really an optimized up to building codes and so on, and you swap in our system, which is called the Rittmann floor system. So we will of course use this aspect that 40% is in the floors, and then on the right, these kind of percentages that we get. For those of you paying attention, and it's rather obvious, it's not 70 and 90 anymore. That is what we realized in high-low, because we only needed in that specific case 30-minute fire resistance or fire rating. Here we're talking about a medium high rise. So this is engineered and calculated for a 120-minute fire rating. So you can imagine that you need a bit of compensation to deal with these kind of things. So if you were to do that, if you flip your floor, if you swap your floors with the system that I'm describing here, then for this one building, you would save almost 10,000 cubic yards of concrete for this one building, right? Which translates to more than 1,200 concrete trucks that would not have to go to this one building site. But also on top of that, as I pointed out, you would save more than 14 miles per story in reinforcement steel, which very nicely and coincidentally, if you were to roll it out, would go from Zurich, Switzerland, where I live and work, to Brussels, where I'm proudly from. I don't know what that is. It's a bit over 600 kilometers. So where would that take us from here? Typically, I try to look it up and I forgot it. In the airplane, I had no connection. Otherwise, I would tell you it's from here to Auckland. No, I don't know. I say whatever. Anyway. But it's not about volume. So I told you this is what really matters. It's the embodied emissions. And let's now see what all the things that I talked about, how it really directly contributes here. So getting the geometry right gives you two things at the same time, right? It's not just about reducing volume, but it's also about lower stresses. So by just going to a lower strength concrete, you reduce the embodied emissions by another 20%. So that gives you this 3/4 on the embodied emissions. But then if you use, and I very loosely call it material innovation, because this is already ready, available in the market. It's these concretes that don't use only clinker, like the ordinary Portland cements, but use fly ash, other kind of trickeries to reduce the clinker percentage in the cement. That allows you a very easy additional almost 70%. So that means that on the concrete level, we have reduced by 91%. Again, the steel, it's the same steel. So there we said that we had a reduction of 80%. So that means that swapping those two results in a solution that is today ready for the market, 15% of the global warming potential compared to your typical floor plate. So for a very banal element. And now we are indeed, based on this, we are with industry a couple of months away of actually launching this as a commercial as a commercial endeavor to offer this for the market. But we will offer this as a prefabricated, dry assembled, low strength concrete. So all the aspects that I talked about that we basically presented in the bridge, those ideas are coming together with the efficiency of the shapes and so on to really offer something that can click in place, be very fast assembled and so on. This is not just academic, but I can unfortunately not show too much yet because we need to figure out how we can make this into a business. So IP still is a bit of a challenge, but I want to nonetheless show you this project. I just got a call, in fact, this morning on my way to the thesis hotel here on campus. I got a call that we already submitted this for building permit. What you're looking at is a very early sketch of a 130-meter tower in Brussels that has been entirely designed around this floor system. So what a luck that I found an architecture and design team and a client that wanted to go for a system that has these outlooks of being disruptive, but before it is on the market, so with all the unknowns of kind of and so on. So I'm very pleased of that. But why I show you this image is also because where typically structure used to be, we're starting to use these cavities to optimize the floor-to-floor heights, and so we offer more real estate to our clients, and so also there we are kind of using all of these things. So realizing that more than 40% of all these buildings is in their floors. That is why we're doing this. As a last point, I'm fully aware that most of these New York cities in the world will not be where I live, but will be in Africa, in Asia, and so on. And that is where I want to end with showing that, because sometimes it looks like what I have to present, yeah, okay, but this Swiss guy, they have too much money, that's why they can do it like that. That the same concepts work in very, very different contexts. And this is a commission that we have received from the Department of Environmental Affairs of the Republic of South Africa, where they actually want us to do something with this beautiful material that they have developed. So this image here, it looks like a good image, like nice green and so on. It's actually representing an absolute disaster in the entire continent of Africa. These are all non-indigenous trees that that suck the ground dry. This used to be a lake that cause a total loss of biodiversity and so on. So already in the time of Nelson Mandela, there has been a national program to cut all of these problematic trees and bushes and so on to bring back the local species and biodiversity. But so what to do with all this biomass? So a small group in the Department of Environmental Affairs under the lead of Stephen Lamb developed this concrete-like material that uses all this scrap as aggregate replacement. So the less cement you put in this mix, of course, the least strong this material is. So they have been using these kind of low impact material mainly for fill-in walls or for stay-in-place kind of cavities in floor structures and so on. But why they got in touch with us, I hope at this point, you see where we are going with this, is that we can activate this weak, lowest pollution material as structural material. We can take all the reinforcement steel, practically all the reinforcement steel out. So by that, we hit 2 birds with 1 stone. We deal with the environmental impact and we make it super, super, super cheap so that indeed it can serve the purpose that it needs to. It's this low income housing solutions to challenge the status quo. This is a picture that I took not in South Africa, but in Addis Ababa, where they're just trying to build like we do, and they don't have the material. The costs are out of control. And as you can see, there is also some other challenges. How can you make it practically entirely unreinforced? It's to go even more extreme in the references, is to bring these compressive forces down in buttresses. And so we developed this buttressed kind of construction system where the only place where there is reinforcement is in these very deep horizontal transfer beams. So that's the only thing where there is a very small amount of reinforcement. Exciting working in such a context and really do proper co-design is that they brought in, that was the idea of our partners in South Africa, these basket weavers. And so these local basket weavers make the forwards, and after they serve a couple of times, we shred those baskets into the next resources for the next batch. So this is something Joel was asking, are you going to show something that no one has seen or something fresh from off the press? No, sorry. Sometimes I get them right, but more often not. But so this is actually, we have just finalized 2 of the prototypes, 5-meter span, that were the last steps before them building the first demonstrator unit. And so maybe what's interesting to see here is that you see these stiffeners again appear. You see the stiffeners go to 0 to the support. That has something to do with the different conditions that we need to also deal with tolerances. And so we want to make this for the engineers in the room, a structural 3-hinged arch rather than a continuous arch. And then we use the very low strength material as a fill. And so this you see here that we use different gradients of materials as well. And so here a last image that we just got in. So they did on the 2nd arch, they did this, this nice load test, and you see it is actually taking 10 times what it should take in ULS, so as extreme loading. So perhaps it might look colorful like that. As a last statement, I want to throw at you again that the challenge is so big that I think we all need to work on this together. So let's share a bit more and build upon each other's work rather than reinventing the wheel. But in summary, I talked about structural geometry to reduce mass. I talked about bringing back funicular geometry, compression-only geometry to reduce the embodied carbon coefficients of the materials because the stresses are so low. I talked a little bit, not too much, but digital fabrication is really helping us on introducing this non-standard structural geometry without the typical associated single-use material waste. I talked a lot about discrete masonry and the potential of circularity with the dry assembly, with the separation of materials that give you that reuse, direct reuse of components or recyclability kind of outlooks. And then I touched a little bit on my belief that in order to really disrupt and bring something different, we cannot do the typical sequential passing on the buck and responsibilities. That is where all these inefficiencies come into play. And I'm not just talking about engineers and architects. I'm even more talking about, if you consider those both as the designers, the disruption between what is being designed and then how it's being done on site. There needs to be much more connection between all of that. I gave you a few hints how we do this through computation, but I think fundamentally that is something we need to do, because that is also the only way we can deal with what Bill Gates calls the green premium, the additional cost of today's sustainable solutions. If you bring them all together, then you will for sure beat the status quo. So with that, this was probably a bit longer than you expected, but thanks for still being here, and I'd be very happy to take any questions.